Welcome to this explainer where we're going to completely dismantle a very common assumption in system design. If you've ever stared at a sluggish, crawling database query and thought to yourself, hey, I'll just add an index, trust me, you're definitely not alone. It's often treated like a magic bullet for database performance. But today, we're going to break down exactly why just adding another index to your table might not actually solve the problem like you expect, and we'll explore what really happens under the hood when your data scales.
So, here's our roadmap for today. First, the great indexing myth, followed by partitioning and covered scans. Then we'll hit the pagination reality check, dive into sorting and offset pitfalls, and wrap up with cursor pagination trade-offs. Let's get right into it.
Starting off with Section 1, the great indexing myth, and how we design database queries for range scans.
Whenever you're facing a slow query, you might instinctively ask this exact question: can't we just add an index? And it makes total sense, right? Adding an index can absolutely help you scan items faster since they use an ordered data structure. It really feels like the ultimate quick fix.
But here's the reality of how this actually works. An index doesn't typically return the data itself, but rather a pointer to the actual data. That means even if your database engine can zip through the index super fast, it still has to take that pointer, go out to the main table, and conduct multiple disk lookups to fetch the actual data.
So because of this extra hop, the overall time complexity becomes log n for the initial index scan plus n for actually fetching those items from the disk. You're basically paying a computational price twice.
Imagine your query has just filtered 10,000 rows from the index. Great! But now your database engine is still required to fetch those 10,000 separate items from the main table. And yeah, although database engines are incredibly smart and use parallel workers to fetch those items concurrently, the sheer volume of disk lookups means the efficiency gained still might not be anywhere near what you expected.
Moving on to Section 2, partitioning and covered scans, where we talk about managing the lookup scope.
In a scenario like we just described, most systems actually use table partitioning, meaning they search on a specific partition based on a partition key. For example, if you're designing a backend for a SaaS application, your database probably holds data from multiple organizations. By keeping separate tables for each organization, you can use the organization ID in your query to look up data only in that specific table. This is a game changer because it drastically reduces the lookup cost since the scope has now been significantly narrowed. Another clever solution is directly storing those non-key columns right inside the index itself and selecting only those specific fields when you make the query. This makes the index return the columns directly instead of just returning a pointer to the main table. We call this approach a covered index scan or an index-only scan. And it's awesome because you bypass those expensive main table lookups completely.
Wait, but there's a pretty massive catch here. Storing all those non-key columns directly in the index means your index size can grow significantly larger, and that directly translates to much higher storage costs in production. So as an engineer, you really have to pause and ask yourself if that trade-off is actually worth it.
Which brings us to Section 3, the pagination reality check, or designing for human limits.
We really need to look at the reality of the front-end user experience here. Do we really need to fetch 10,000 items in any real-life system? Like, can any user actually grasp 10,000 items at once? The answer is obviously no. Well, this is exactly where pagination comes into the picture. In real-world systems, we never actually return 10,000 data rows at once. Instead, we send data back in smaller chunks known as pages. However, typical pagination techniques are offset-based, which have their own drawbacks.
Let's jump into Section 4, sorting and offset pitfalls, and the hidden cost of ordering. So, even with pagination, we still have to order the full data set before we can accurately skip to the right page. If you're scanning a huge amount of items, doing this sorting in memory is going to consume a massive amount of server RAM. It literally creates a major performance bottleneck for your system.
Obviously, we need to eliminate this in-memory sorting. And to fix this memory drain, we can just introduce an index directly on the sort parameter. Since indexes are inherently ordered data structures, the data is naturally retrieved from the index already sorted. That means absolutely zero in-memory sorting is required by your database engine.
Now, you might think you're totally in the clear. But there is a massive trap waiting if you're using the typical offset or skip command to navigate those pages. The job is far from done.
Let's say you have a query filtering 10,000 items, and a user clicks to fetch the very last page. If your page size is 100, your database has to skip 9,900 items just to return those final 100. And here's the fundamental flaw of offset pagination. A database cannot skip items it hasn't looked at. It literally has to scan and count through all 9,900 items just to throw them away and give you the last 100. That's just wild.
And this perfectly highlights a vital metric in database monitoring known as the returned to scanned ratio. This metric basically measures how many items were actually sent back to the application versus how many the database was forced to read. In our offset scenario, returning just 100 items, but having to scan 10,000 gives you a totally terrible, highly inefficient ratio.
That takes us to our final section, number 5, cursor pagination trade-offs and how we actually fix this ratio.
To solve this massive skipped item issue, real-world systems often move away from traditional offset-based pagination and embrace a really popular alternative, cursor-based pagination. Here's how it works. Instead of telling the database to skip 9,900 records, a cursor tells the database exactly where to start reading next. It's like saying, hey, start fetching 100 records immediately after record ID 9,900. This drastically reduces the gap between scanned and returned items. You completely eliminate the need to scan through thousands of skipped rows, keeping your database lightning fast no matter how deep into the pages a user goes. But you know there's always a trade-off. The catch here is that you lose the ability to jump to random pages, because you need the exact cursor from the previous page to know where to start the next one. You can't just give a user a button to jump straight to page 10. You are strictly forced to sequentially iterate through the pages, usually by just providing next and previous buttons. At the end of the day, every architectural decision is just a balance of trade-offs. The indexing myth is officially broken. There are simply no magic bullets here. So the next time you look at a slow query and think about just throwing another index at it, ask yourself, what hidden cascading trade-offs are you really triggering under the hood of your database architecture?